Okay, hello. Welcome back. Um, the topic for today, you will learn more about classification and also uh, decision boundary. Um, so we actually learn a little bit about classification when we study decision tree. Basically, you have your data and you want to um, make a decision about what the data is. So that is the basic idea of classification. So why do we begin classification, right? So suppose there is a fish canning factory. Uh, mm, mm. So suppose there is a fish canning factory. Basically, the fisher catch fish and want to put fish in a can, right? Now, when you catch fish, um, you cannot just pick which type of fish when you want to catch, right? Normally, you get a lot of many type of fish, and you have to separate them, right? Because you have like a can of sardine, you have a can of trout. So you want to be able to separate these two fish, right? So at the beginning, what we have human, right? A human will go to each fish at a time and make a decision if this fish is a sardine or is a trout, right? So it's basically a sorting process, right? There's a sorting um, facility that um, you have people work on in the in the factory. So as time go by, you catch more fish, and basically you need more people, right? You need more staff to be able to sort out um, two fish, right? And there can be many more fish, right? Not just these two. And it may be more cost efficient if we have like a robot arm, right? Basically, the robot arm will pick the fish and then put it into the correct bin. So basically, we have a sardine and then we have a trout. And this robot hand, well, you can put a camera on the robot arm and the camera will see the fish, right? And after they see the fish, they have to be able to recognize if it's a sardine or if it's a trout. So now the question becomes, how can a machine be able to distinguish between these two examples? So at the beginning, um, we have a programmer, right? And we can program uh, the fish, the sorting process of the fish, right? You can code it, right? So for example, you have this simple if-else structure. You have if the length is between 10 and 30 and the weight between 1 to 5, then you say that is a sardine, right? Anything else is going to be a trout, right? So is there a problem with the programming? I mean, it works, right? Basically, it works. It can sort out the sardine and a trout. But the problem with the coding, right, is that you need some kind of information. You need to know the physicality of the fish, right? You need an expert to be able to come up with this condition, right? And there are many questions that you can ask, right? Why this number 10? Why this number 5, right? Where are this number come from? And this number can come from observation, right? Basically, they can just go to the factory for a day, and then you look at all the trout, and then you measure, right? And then you just take the minimum and maximum for that day, and then you have a code for sorting the trout and the seed. So we have some kind of coding, right? We can use observation to help defining the number, right? It's basically a boundary, right? You have this boundary that each of the class will fall into. And this can raise some of the issue, right? The question is our knowledge complete? What do I mean by complete or incomplete? So do we have enough data, basically, right? When we make a decision that, okay, the length has to be between 10 and 30, have we seen all the trout in the world, right? And not only that, what about the future, right? Maybe because of the global warming, the trout will shrink like one centimeter every year. And so you have to adjust this number like as the times go, right? So it has to be some kind of like dynamic. You cannot just hard code the number and expect it to work for a very long time. Another one is the robot program might end up to be very complicated. Right now it's very simple, right? It's very simple. But there might be a trout that have this kind of condition, right? We have like a very big trout or very small trout that fit the description of the study that we have written. So to be able to separate them, we need to add more conditions, right? So the closer the objects are, like between classes, the more condition you have to introduce in your programming. So when you have more condition, your program will become much more complicated. And when you want to make changes to the program, right, it's gonna be very hard, right? Think of like you have maybe like 20 condition, right? And the condition is not just maybe just if condition 1 and condition 2 and condition 3. It can be like nested if, it can be like many more structure, right? Complex structure when you write code. So that is some of the issue. And another one is, right, it's not adaptive, right? Because when you write a program, right, when you write a program, the program cannot be changed, right? Once you like compile them, it's gonna stay there. So we want to be able to have something that can be future proof, right? So we want to be able to be able to update the program without much trouble. So that's why we want to come up with a way to be able to learn something from the data and make decision about it. So between study and trial, there are some physical characteristics that we can measure, right? For example, you can measure the length, the weight, also the color, and also the body pattern, right? And we want to find this relationship, right, between each of the measurement that we do. In mathematics, right, these are the feature, these are the input, and the fish category, which we call a label, would be the output. And the machine learning is basically you want to find a function. Right? You want to find a function that map the characteristic to a fish category. So if we write in more formal way, right? We have our data. What is our data look like? It's going to be a feature label pair, right? X is the feature, right? And then Y would be the label. And well, X would be lying in m-dimensional space, right? Which basically we have m features. And then for Y, we would have a number associated with the class, right? So we have class 1 to class K. And a classification task is to infer a real value function, fx, that map the feature to its corresponding label with high accuracy. So the task is not just finding a function, but we want to find a function that has high accuracy, right? So how can we do that, right? So if this function, we would call it a classifier. And each classification model have different functional form, right? And then you want to adjust the function parameter to account for the learning part. So basically you have this function, right? And then when you have the data, you can just put the data and it's gonna spit out the output. And if you want this function to be adaptive, you need to have some kind of parameter, right? You need a parameter to control a function. And not every model have parameters, right? For example, decision tree does not have parameter. KNN does not have a parameter. But in this class, for today, we will look at the function that have parameters. So defining function is one task. Adjusting the function parameter is another task. So the final goal of the learning, you want to minimize the error, right? So what is the error? The error is when you predict incorrectly. And we can write the error using this delta function. Now, delta function, right? Basically, you have a condition inside. It's a logical expression. And this delta function will return 1 if whatever inside is true, and will return 0 otherwise. So the condition that we have is we have the label yi is not equal to the output of the function of our model. So if the expression, the logical expression inside is true, it means that our prediction is different from the label, right? So we will have a 1. So this is just, you just accumulate, right? You sum up all the mistakes you make, right? If you make a mistake, you get 1 penalty. And then you take the summation. So this is a classification error. That is very, very simple function, right? If you make a wrong prediction, you add 1 to the error. Now for regression, right? Regression, we have Y that can be a target, right? Y is a target. But for classification, we have Y to be a class label. And in classification, right, Y is a real value, right? Basically, you want to have a model that can explain the data. So Y would be a real value. And this real value can be transformed into a decision, right? You can say that if Y less than some threshold, you will predict to be like class 1. And if it's not, then you will predict to be like class 2, right? You can also use regression as a classification task. Now, there are two types of function that we can study. You can learn a linear function and a nonlinear function. Now, for the linear function, we assume that the data is separable using a linear decision boundary. So if we plot the data, right, you should be able to draw a line that one side of the line would be one class and another side of the line would be another class. And this, the algorithm for linear decision boundary, we have this square classifier, we have logistic regression, we have support vector machine. And for nonlinear, basically you draw a line as well, but it's not going to be a straight line, right? It's going to be like squiggling, depending on the definition of your function. You can have like SVM, the support vector machine with kernel neural network assemble, and so on, right? So today we will focus on the linear part. It's easier in the way that you can write the equation and you can visualize it. And then later on, maybe toward the end of the course, you will learn more about the nonlinear function for classification. So we decide on the linear part, right? We have our data. We want to find a linear boundary. So for the linear part, right? Well, the decision between linear and nonlinear will be based on the data, right? You need to understand the nature of the data to be able to pick which model you want to use. And each one of them will have like pro and cons. Like for example, in linear case, it may underfit the complex data. But if your data is very simple, but you use nonlinear, it might overfit in the simpler case. So to be able to pick between linear or nonlinear, you have to understand the data. But if you don't understand the data, what would you do? Which one would you pick? If you don't know anything about the data, like maybe someone just give you the data and make you to create a classifier. Well, in research, you actually try everything, right? What I mean by try everything, in most cases, you start with linear function, right? You start with something very simple, and this simple classifier will become your baseline, right? So when you write a research paper, you publish your own method. You have to compare it to something, right? And that something is the baseline. In most cases, if you are working with the a classification problem, your baseline would be the linear model, right? Mostly is SVM, right? You try SVM, whatever number you get, that's your baseline. And if you want to be able to publish that paper, your algorithm have to beat the baseline. Basically, you need to have a higher accuracy, right? And then you start trying all the linear, and eventually you will go to the nonlinear part. So that is the strategy, right? You start with linear, and then you move your way forward to the nonlinear. So the classifying tasks, there are actually many type, many way to classify. The most common way is the binary classification, right? For the binary classification, basically you have two classes, right? You have two classes, and then you want to decide which data belong to which class. Now we have multi-class classification. The multi-class classification, right? You have your data, you have more than two class. You have at least like three class, and one input can belong to only one class, right? So in multi-class, right, when you put the label, you have to pick which class it belongs to, right, in multi-class. And this is the ground truth, basically the ground truth. The model that you develop, right, you want your prediction to be as close to the label as possible. So your prediction is not the class, it's not the class number. Your prediction will have the same number as the ground truth. So in this case, you have three classes. Your prediction would have three number. And this three number is basically tell you the score or the probability that this data belong to one of the class, right? So for example, you can have like 0.1, 0.1, 0.8, right? That is your output of the function. You have three number. And then you can compare this to the ground truth, right? So if your prediction if your prediction is perfect, it's going to be 0, 0, 1. But if it's not perfect, it's going to be any number that can sum to 1, right? And then you can compute the accuracy using the difference in the vector. So that is multi-class, right? So one example, you have to give out many answers. For multi-label, you also output each number for each class, right? The output is the same as the multi-class, but now the sum of the number that you output can be more than one. So one object can belong to more than one class, right? For example, we have this image that belong to class 1 and class 3, right? And your prediction, it can be like 0.9, 0.7, 0.8, right? It doesn't have to be sum to 1, right? So it will think of each class separately, right? So that is the difference between multi-class and multi-label, right? Multi-class, only one class per object, but your answer need to include three number. Basically, you have to compute the property of this object belong to each of the class. In multi-label, it's the same concept, but one object can belong to more than one class, and your answer doesn't have to sum to 1. And this multi-class or multi-label are often used in medical because, for example, you have like your CT scan, right? And you want to be able to diagnose some of the symptoms. And for one image of the CT scan, there can be many symptoms, right? You can have like many diseases at the same time, right? So that is the multi-label. We also have one class classification. So what is one class classification? So one class classification is that you only have one type of object, and you want to classify if that data is that particular class or not, right? So it's different from binary. In binary, you have exactly two classes. In one class classification, you have one class and your answer would be yes or no, right? So this one class classification is often seen in detection, like object detection or pedestrian detection. You want to detect a person, like you give the image and you ask if this picture is a person or not. And the way that one class classification train compared to binary is different, right? Because in binary, right, you have two classes. For example, you have dog and cat, right? And when you train both class, you need to have the data of dog and then you have the data of cat, right? You have to have the data for both classes. But for one class, right, you only have dog, right? And then you have not dog, non-dog, right? So this non-dog can be anything. It can be cat, it can be tiger, it can be snake, it can be it can just be random image, right? So for binary, you need to collect the data for each class. For one class, for the no the answer no of the class, you can just take any image, right? Any image as long as it's not dog. Right? And because the negative example are countless, right? Because anything else is a no, right? It's a dog or not dog. And the not dog is very broad, right? You can just put bird, you can put cat, anything can go. So that is one class classification. And then we have open set classification. Now, open set classification, basically you can group, right? It's basically you group the data into class, but you don't have to answer for every data. So some of the data can be like question mark, right? Some of the data can be just assigned to nothing, right? And this is actually more difficult than a regular classification, because in the classification you have this decision boundary, right? And then everything in this area will be one class, anything in this area will be another class. But for open set, you actually have a closed boundary for each class, right? And if the data is not belong to any of the boundary, then it will not be assigned to a class. And so this will work well in a general example, right? You have many class that you have the data on, but then you have new data that you have never seen before, right? For example, you have the image of every animal in your zoo, and then you just introduce a new animal to the zoo, right? This new animal is not part of the animal that you have seen so far. So it cannot be assigned to any of the group. So that is open set classification. So what are the challenges for the classification method? Right? The main one would be the size of the data. Like how many data can you collect? And not only that, it also depends on the model that you pick. How many parameters are in your model? The more parameters you have, the more data it will require. So in model like neural network, right? When they talk about the number of parameters, they talk about like 1,000 or maybe 1,000,000 parameters. And when you have 1,000,000 parameters, you need to have more than million example, right? In general, you want the example to be like as large as your number of parameters. Another challenge is incorrect label, right? When you have millions of data, you need to have a very good labeling, right? It can be from a human how to label image one by one. Maybe you can write a program that help you to label. So it's basically the quality of the data. And this quality of the data is very important because compared to the algorithm, if your data have like incorrect labeling or maybe like imperfect measurement, the algorithm will not save you, right? So even with a very good data, a basic model can perform very well. So that is something that you have to be very about. So that's why there are papers when they create a benchmark data set, right? The data set that like every algorithm will use, they have to write a paper to explain what are the quality of the data, how they come up with the label, and so on and so forth. Another one is class imbalance. This class imbalance is actually very crucial because, for example, in binary classification, you have two classes, right? And if you have the same number of example in two class, you can learn both class very, very well. But if you have one class, like 80% of the data to be one class and 20% to be another class, your learning algorithm will lean toward this 80%. And it's gonna make the baseline very harder to beat because if you have class imbalance, without looking at the data, you can just predict that it's gonna be in this class. And you are right 80% of the time. So your algorithm have to be able to have like more than 80% accuracy. And to fix the class imbalance, there are things called data augmentation. In data augmentation, basically you try to transform the data a little bit, but you keep the same label. Right? For example, in image, right? You have image of a bird. Let's say you have image of a bird, and then you flip it, right? You flip the image of the bird, right? So now you have two data with the same label, right? So this is data augmentation. So for the class that you don't have many images, you can just do this. Like you can also rotate by like 1 or 2 degree, and then you have like 300 more images if you rotate all the way. Right? So that is how you fight class imbalance. by using data augmentation. So what are the real world examples? For computer science, in the very first application of uh, machine learning that can do a classification is going to be the spam email detection, right? So the email that you get is going to be checked if it is spam or not, and then it will go directly to the junk mail, right? So that is the introduction of the classification to the world, right? The first application would be in the spam mail. And then we have expand the classification into a medical application. And this actually helped with diagnosis disease, right, based on the patient data, allow early detection and timely intervention. And for medical diagnosis, normally it will be done at the beginning stage. And then after the algorithm make a prediction, the real doctor have to confirm the result because you cannot rely on uh, the machine alone because the accuracy is not 100%. So there are room for error, and then you need to have an expert to actually double check the work of the model. And I think for now, like right now, um, in many hospitals, they would have some kind of like a chat application that you can chat with an agent, right? It's basically, it's gonna ask you all the data that it needs, and then it's gonna make a prediction whether or not you are like having this symptom, you have have this disease or not, and then it will decide whether or not you have to go to see a doctor. And then we have credit card approval. So they actually come when there are a lot of fraud, and also there are more use of the credit card. And to be able to uh, decide whether or not this person is qualified to apply for a credit card or not, they would have some kind of like a model that can make a prediction whether or not this person will pay back the loan in time or not. In financial institution, they use classification to do the automatic approval process, right? So they're not use human anymore. When you apply for the credit card, you can apply online, and the process of like verifying whether or not like you are the real person, you can pay back, you satisfy all the condition, it's going to be done by a program, and then you just wait for the credit card to arrive at your house. Another example would be image recognition in autonomous vehicle. You probably seen this example a lot in this day. Basically, it's the self-driving car, right? They use image classification to be able to detect sign, detect a person, or detect obstacle, or detect auto vehicle. And the challenge for the self-driving car is the variety of object, right? Because the sign, right, for example, the stop sign in each of the area would be like slightly different. So they have to account for some variety. And also to detect auto vehicle, there are maybe more than like 1,000 type of vehicle. And then you have to be able to distinguish between vehicle, a building, a person. So that is also a very difficult task. And despite all that, they have to do navigation as well, right? So it's become a decision-making process, right? Given this image, what is your decision? Will you hit the brake or will you hit the speed pedal? Do you have to turn the wheel left or turn the wheel right? Right. So for each image, they have to make a decision. So it's kind of like a classification, right? You have this image. This image is the image that you have to turn right. This image is the image that you have to stop or something like that. So it can be framed as a classification problem. Sentiment analysis. So in social media, you can use sentiment analysis to help understanding the feedback of your product. It's basically it read the text from like Twitter or Facebook, and it's gonna make a prediction whether this text is positive, negative, or neutral. And for each type of sentiment, you can like make a marketing decision, right? Whether or not, okay, this product receive a lot of negative, what's wrong with it? And then you can plan how to fix the negative comment. And so for sentiment analysis, because you focus on the positive or the negative, mostly it's gonna look for a keyword, right? Does it have the word not? Does it have the word like? On and so forth and so forth. So most of the sentiment analysis algorithm is usually based on semantic, based on the text, based on the word, the keyword, right? And maybe you have some keyword together. Um, for example, if we say like not, like, right? So they have the word like, but they also have the word not, and they had to be together to be a negative comment, right? If it not is negative comment, if it like is positive comment, but when it combined together, it become negative comment, right? So there are these special case that you also have to handle for sentiment analysis. So let's start with our first, not the first, but like second algorithm for classification. We learned decision theory before the midterm, and now we will learn more about how to make a decision boundary. So we have our data, right? We have this yellow dot and the purple dot. These are our data. And then our data have two classes, right? Yellow and purple. And a decision boundary is an imaginary line, right? It's basically you draw the line, and one side of the line would be one class, another side of the line would be another class. And your objective is to actually find this line. So for linear classifier, this line would be like a plane, right? So this W, right, is basically the slope, right? The slope for each of the dimension. And it also inform our vector, right? So basically, what you want to find a vector. So basically for this line, the vector is going to look like this. And you want to multiply the vector with the data. And this will give you a positive number or a negative number. It's basically you dot product to vector, right? So this line and this vector have the same number, right? For example, you have like 1, 1, right? So if you write a vector, you have this 1, 1. And the data that are all the point that are above this line, when you do the dot product with this vector, you're gonna get a positive number, right? Right. For example, you have 1, 1, and then you have 2, 2 here, right? you have let's say what is this is 1 0 or it's negative 1 0, right? So for 2 2, right, you multiply with the transpose, right, you get 4, right? You get 4, right? 1 times 2, 1 times 2, and then you add up. For this example, right, your decision boundary is 1 1, and then you multiply the point here, right? So you get -1 plus 0, and then you get -1. So what you care about is the sign, whether or not your result is positive or your result is negative, right? And because when you do the dot product, basically you do like, so for example, a dot b equal to ab cos theta, right? So it's basically the cosine that will determine the sine, right? So for a small angle, right, if um like if the point is pointing to about the same direction, you will get a positive. You will get a positive sign. And if it's like a very a very big angle, you will get a negative number. So in the cosine curve, right? In the cosine curve, right? You would have something like this, right? So you have the negative, and then you have the positive. So for this, right, we have W transport time X. The W is our vector. It's basically a decision boundary, right? This is a number that represent a decision boundary. It's a vector. And we only take the sign, right? It doesn't matter what value you get. You can get 4, you can get 7, but at the end, you only take the sign, right? So if it's 4, you get +1. If you get 7, you also get +1. So it's going to be either 1 or -1, right? So one is the one side of the decision boundary. Another side of the boundary would be -1, right? So the prediction, right, is right here. So if you have anything that is less than 0, you predict -1. If it's greater than 0, you predict 1, right? And that is the model, the function, right? So basically your fx would be equal to the sine of the dot product between your parameter vector and the data. So for example, right, I have the vector W to be 2, 2, the vector of 2, 2. And for the violet point, right, the violet point is 1, 1. If you do the dot product between this 1, 1 and 2, 2, you will get something greater than 0. But for the orange dot, you will get something negative. You get a negative number, so your prediction would be -1. And so with this setup, right, if you want to use this in the binary classification, basically one class would be 1, another class would be -1, right? So you want to use 1 and -1 for your y, right? Either one of these. Okay, so we have our function, right? We have our function. Now, there is slightly complication is that all of this green line, of this green dot, if you dot product this green dot with the vector, with the W, you get 0. So what happens if you get 0? Right? So you say, if it greater than 0, you get class plus 1. If it's less than 0, you get class minus 1. But what about it's exactly 0? So when it's exactly 0, you cannot predict. Right? It's basically is we are very unsure. Right? We are not sure whether or not this data or this example would be, in the positive example or negative example. And every point that give you the 0 answer, if you connect them together, you will get a decision boundary. That is the boundary between the positive example and negative example. So the line that form a decision boundary is the line that when you dot product with your parameter, you will get 0. So a set of point where this becomes 0, it will define a decision boundary. So in geometry, every point that are like the line that are perpendicular to the vector will give the dot product 0. Right? If your vector is here, if you draw a line that is perpendicular to your vector, this line is the line that become the decision boundary. It will have the dot product equal to 0. Another thing to note is that the size of the W does not change the decision boundary. It doesn't matter you have a very small W or very big W. As long as it points to the same direction, you will have the same decision boundary because it only care about the dot product, right? So if the dot product is 0, right, you times 100 on both sides, you still get 0, right? So if you use like W transpose X equal to 0, then 100 transpose X will also be 0, right? So it doesn't matter the size of your vector, it will have the same decision boundary. And because of this, we can actually scope our function, right? Because if we have, let's say like this, like 1, 1, 2, 2, 3, 3, all of these give the same decision boundary, but it's different solution. And when you have different solution, you have to be able to evaluate which solution is better. And because they are equally the same, we can just make sure that our weight will have one norm, right? You want weight to be fixed number so that when you get the answer, all these are the same answer. And then you don't have to compare each one of them, right? So in the decision boundary, the vector that will explain the decision boundary is often have the norm equal to 1. So intuitively, we are more certain about the prediction if the point is far away from the boundary, right? So I have the boundary here, I have the purple point here, and then the orange point here. So when I make a prediction, of course, the purple point would be positive, the orange point would be negative. But I am more confident that the orange point is negative than purple point being positive. So the distance between the point and the decision boundary matters, right? Because as it gets closer to the decision boundary, it means that this data is getting closer to another class. And when it hit exactly the boundary, you get the dot product equal to 0. And that's where you are very unsure. And because of this observation, right, being the distance from the point to the decision boundary also matter, we can start making an evaluation, right? So, for example, for this data, I have 4 solutions. I have 3 solutions, right? I have green, blue, and red. All of these lines separate the data, right? Separate the purple and orange. The question is, which one is the best line, right? Now, how would you pick the line? Which one do you think would be the best? 1, 2, or 3? Right? Each solution is a valid solution because it can separate the data. But we want to find just one that would be, considered the best. And when we want to consider the best, we want it to have the line that are furthest away from the data of both classes. So what we are looking at, we look at a margin. In the green line, the closest point is around here, right? Right. So you have this closest point. What about the blue line, right? The blue line, we have something like this. And then the red line, maybe around here. So as you can see, right, the red line have the largest margin, right? The closest point to the red line is further away than the closest point to the other 2 lines, right? So you basically you compare this number, right? You compare these 3 numbers, and then you just pick the one that is the largest. And so not only that your decision boundary have to be able to predict correctly, but your decision boundary have to also maximize the margin. So there are 2 tasks for the decision boundary. So how can we calculate using mathematics, right? So we have our decision boundary W. We have our decision boundary W. You have the point X, right? You have the point X. You have a point. So basically, if you want to find the distance between the point and the line, you draw a line that are perpendicular, right? You draw a line from the point to the line that you want to calculate the distance, and then that line has to be perpendicular to the line, and these are, right? This R is going to be the distance. So basically, you can represent X in terms of the sum of 2 vectors, right? So you have XP. XP is this vector, right? XP is this vector. And then you have another vector here. And this vector is actually parallel to your W. So basically you sum up XP plus this vector. But because this vector is parallel to W, you can convert W to be a unit length. So this is a unit length vector, right? You get the unit length vector, and then the distance is R. So you multiply the distance. So this X is basically a sum of two vectors, right? XP and then R times W divided by the norm of W. So we have this equation. Now, if we want to make a prediction, right? We want to make a prediction about this. We actually multiply our vector, right? Basically, you dot product, right? This is a vector. You want to make a prediction, right? So you calculate this one, and then you multiply the weight into other term, like these two terms. And something that you notice is that XP is on the boundary decision. So this term would be equal to 0, right? Because XP is on the line. So the dot product between W and XP is 0. So basically, you would have this equation, right? W transpose times R, W over W. And so these are, right? You have W transpose X, right? And then divided by the length of the W. And R is the distance from the line to the point. And so this I become a margin. So for every point, right, if you know the decision boundary, you can calculate the margin, right, the distance from the point to the line. And we want to maximize this margin, right? So we want to maximize this equation. And so the margin in this case, right, is the distance from the closest point in the class to the decision boundary. So in our data, right, there are many points, right? There are many points in data. When we define a margin, we only look at the closest point, right? So for example, if you have the red line, right, the closest point would be this one. So this R of this point is the margin of the model. Right? We don't care about the margin of other point. We only care about the margin of the closest point. Similarly, if you look at the purple example, right, the closest one would be here. So you have the another R, right? So you have a margin for positive class and a margin for a negative class. And when we have the margin, right, we can now do some optimization, right? So if I change the line a little bit, right, the margin will also change. So we can find a line that maximize that maximize the margin. So the margin basically it is the geometric margin. And because if we fix the length of the boundary to be 1, it's basically just this value, right? If the denominator is 1, then you only get this. So what we have here, right? If x plus, let's say the nearest point in the positive example is x plus, and the nearest negative would be x minus, then the dot product between the decision boundary and the point, you will get +1 and -1 respectively. Right? So right now we only care about sign, whether or not it's positive or negative. And so what we do is we want to compute the total margin, right? Because we have two margin, right? We have margin for the positive and then we have the margin for the negative. And we want to optimize them at the same time. So what we do is we compute, right? We have the margin. So basically we want to add these two distance together. Now, if you want to add the two distance together, right? What you want to do is you want to use the absolute value, right? If you want to get just the distance. But because the decision here also come with a sign, so we can just add a positive example and then you subtract the negative example and then you take the average. So the margin is basically the average between the margin of the positive example and the margin of the negative example. And if we add them together, right? If you average them together, you will get this 1 over the weight. So what does this mean? Right? It means that the margin is actually depend on the size of the vector. And why that is okay, we have to be able to introduce more constraint, right? So we need to find W that maximize this, right? And not only that we want to maximize this, we also have this condition that for every positive example, the dot product has to be greater than 1. And for the negative example, you want the dot product to be less than or equal to 1. So what does it mean by +1 or -1 here? Because before we said that if it's greater than 0, it's positive, right? If it's less than 0, it's negative. Why do we have to make it 1? And the reason that we have to make it 1 is that we want the boundary to have a margin, right? So if this becomes 0, is basically your boundary would be a very thin line, right? Everything here would be positive, everything here would be negative. But if you have plus one and minus one, what it means is that you still have the decision boundary, but the positive example will start when you are at least 1 unit apart from it, right? So you have the positive example, and then you have the negative example, right? So you have this band, right, of nothing, right? There should be no point in that band, right? And what we want is we want to increase the size of this band as much as possible, right? We want to push the point further away from the decision boundary, because the further we push apart, the more confident we are about making the prediction, right? And so here we only want plus one and minus one, and you want to make sure that the W that you got like satisfy this condition. So this become a quadratic programming problem. So this called SVM, support vector machine, and this SVM it want to do two things, right? In the objective function, it want to minimize this expression, right? Now this expression, minimizing this expression means that you want to push the point further away from the decision boundary, right? Because we learned that the margin is based on the size of the vector, right? The lower here, right? So the margin, right? The lower the weight, the lower the size of the vector, the higher the margin, right? So we want a high margin. So we want to decrease the weight. But by decreasing the weight, you want to make sure that the weight that you decrease still predict correctly. And we have objective, we have constraint, we can actually combine both objective function and the constraint into one big objective function. So this is the same objective function, and then we transform the constraint into this. So how do we read the equation on the right? So you have the summation from I to n, right? And then you take the maximum between 0 and 1 minus yi times the dot product between the vector and xi. So what does this equation mean, right? So we start with this part first. What is this? What is the dot product between the vector and the point? So this is the prediction, right? It's the prediction. What about yi? What is yi? Well, yi is the label, right? It's the correct answer. right? You know that this example is positive or negative. Then why do we multiply them together? Right? So for the label and the prediction, so if the label is positive, the prediction is positive, right? So you have this combination, right? You have this combination, right? So you only care about the sign. So when you multiply the label with the prediction, you will have either positive or negative, right? What are the scenario that you get a positive? You get like this entire thing is positive for this case and this case, right? Right? Positive times positive, you get positive. Negative times negative, you get positive. So what does it mean by these two cases? It means that your prediction is correct, right? When your prediction is correct, you have the same sign, right? Between your prediction and label, you have the same sign. So when you multiply the same sign, you get a positive number. And if you predict incorrect, right, you will get different sign, right? One would be positive, one would be negative. And when you multiply them together, you get a negative number, right? So if you are correct, you get a positive number. If you are incorrect, you get a negative number. And you take one minus, right? You take one minus. So if I predict correct, what would I get? So if I predict correctly, I will get a positive number, right? So one minus a positive number, right? You will get a very low number, right? It can be if it greater than one, then you will still get zero, right? Because we take the max between zero and this expression. So for the correct, you get the number that is close to zero, right? Very small number. If you are wrong, you get a negative number. And one minus negative number, you get a number that is more than one, right? Because when you subtract a negative number, it's basically you plus, right? So you have the number that is more than one. So we want to minimize, right, this entire expression. So when we want to minimize this expression, we want this term to be very small, right? That is the minimization that. And when this becomes small, you want a lot of correct, right? Because each correct example that you predict correctly, you will contribute a very small number. But if you predict incorrectly, you contribute a very large number. So this equation, basically, it will maximize the accuracy, right? Because if you are correct, this one will be very small. But if you're incorrect, this one is very, very large. And so the combined equation, right? Basically, you still want to minimize the margin. You want to maximize the margin, but also you want to also maximize the accuracy. So that is how they transform the condition into the objective function, right? It's a clever way, right? By multiplying the label and prediction, you get a different sign, and that can become the cause of the objective function. And there's a name for this term, right? This term is called a hinge loss. And this hinge loss is an approximation of the 0, 1 loss function. So at the beginning, right, when we start with the model, we want to minimize this function, right? You want to minimize this function, right? This function, you just count the number of incorrect example, right? If it's incorrect, you add 1. If it's incorrect, you add 1, right? But this function is the green line, right? This 0, 1 loss function is the green line, and then the hinge loss is the blue line. So as you can see, the blue line is actually like more smooth, right? And you can take the derivative of the blue line because for the green line, like you have these points that are not differentiable, right? Because the slope is undefined at that point. But for the blue line, you can dip at every point. So that's why they use the hinge loss as an approximation to the 0, 1 loss function. Right? So in reality, what we want is we want to use this function here, but because this function is very hard to compute the gradient, that's why they use the hinge loss instead, because the hinge loss is easier to find the gradient. Right? And then the hinge loss is minimum when the yi agree with the prediction. Right? If you have the same prediction, you will get a number that's equal to 0, so it's minimized. So the turning point that are the nearest to the decision boundary are called support vector. Right? It's the one that support the boundary. So this point, these 2 points that are closest to the decision boundary for each positive example and negative example, we call it a support vector. And what happened if we have the data that is not linearly separable, right? For example, I have this data, we have the black and gray. Like we have the class that are black and then another class that are gray, right? Can I draw a line that can separate black and gray? Well, I cannot, right? Because they are not in a very good shape. So when your data look like this, when it's non-linear, well, you can use the non-linear classifier, right? Basically, you just use another method, right? You cannot use SVM. SVM only work for the linear data. Now, if we want to like very persistent, we want to use SVM. We only know how to use SVM, but the data is not linear. What can we do? So another approach is to transform the data into a richer feature space. So what do we mean by richer feature space? So if the data cannot be separate in 2D, we might want to transform the data into a higher dimension, right? Maybe the data can be separate in 3D, right? In 3D, you just cut the plane and perhaps there are some property that can separate them. So basically, we want to we want to transform the data using some of the function. And this function have the name is called kernel, right? So a kernel is a function that transforms the data into a higher dimension. And the choice of the kernel, there are many choices of the kernel. You can look at in the SVM package, you will see a list of kernel that you can choose. And each kernel is basically, it will add the new dimension to your data based on the function that you compute, right? So in example, right, you have this data, right? You have x1, x2, you have the red, and then you have the blue, right? If you want to separate them, you cannot, right? But if you use this kernel, right? For example, x become x1 square, y become x2 square, and z become x1 times x2, then you have the red point here, and then you have the blue point here, right? It's still the same data, but now the data move to 3D, and you can have the decision boundary here that can separate the red and the blue. So basically, what we do is we transform the data so it can be separate by a linear function. And this is very common in computer science. We try to transform something that we don't know how to solve into something that we know how to solve. And this is one of the examples, right? You transform the data. So you may have seen this type of question in the midterm exam. When they ask about the regression, I have like four feature, and then I ask like which one is suitable for regression and which one is not, and how you would want to fix it. And the way to fix it is to just transform the data. So there are many types of kernel. You can watch the video about the polynomial kernel. I'm not going to go into the detail of the kernel function. So what about overlapping data, right? So what do I mean by overlapping data? So there might be a case when you have the positive and negative example at the same point. It is possible, right? So how would you handle this kind of situation, right? Sometimes it's just the data, but sometimes it may be noise in your data that somehow make the negative example and positive example to lie on the same spot. So if they are in the same spot, we have no solution, right? Because SVM, we want this to be correct. We want this constraint to be correct, right? So if the point is both positive and negative, and the same point become both positive and negative, then this condition will never be satisfied. And so what we have is we need to relax a condition, because our condition say that you have to be able to separate them absolutely. But in reality, well, you cannot, right? And when you cannot separate them like completely, it's gonna mess up the margin, right? Because let's say you have this decision boundary, right? You have this positive example, and then we have this negative example. What is the support vector for positive example? Is it this point? Is it this point? Is it this point? Which point? Right? So you want it to be the closest point, right? So let's say this one is the closest point. It's a positive example, but when you dot product with the decision boundary, you get a negative number. Right? And that is something you're not expecting, right? You expect that your support vector for positive when you dot product with the decision boundary, you should get positive number. So because of this scenario, we have to relax the condition a little bit. And the way that to relax the condition is to introduce more parameters, right? So before our parameter is only W, right? We only need to learn W, the decision boundary. But if the condition is too strict, you may not be able to find a line that can separate them. And so what happened is that we add this variable for each point. And what it means is that this variable can allow the positive example to have a negative dot product, right? So let's say for this one, the positive example, right? If the dot product is -1, then you have this variable to be 2, right? So you have 1 minus 2, you still get -1, right? So you can still satisfy this equation by having this variable to be 2. So all this variable is going to be the positive example, right? This also works for the negative example. If the dot product here, you get 1, right? You can also have 2 for this, and then you are allowed the negative point to have positive dot product. And this variable is called slack variable. Right? Basically, it's a variable that allows some breathing room when you make a prediction. And so the objective function changes, right? So before we only have this part, right? This part will minimize the margin, will maximize the margin. But we also want to minimize the slack variable as well. So the slack variable said that, well, you can make a wrong prediction and it still count as a solution. But the incorrectness of your model, you want the incorrectness of your model to be very low. So the lower this slack variable is, the closer it is to be in the original condition, right? So if the chi is 0, it's basically the same as before. But for this, it can be more than 0. And we want to minimize, right? You want to minimize this. You want the condition to be as close as possible to the original, but you can allow some breathing room. So you have this new objective function. And you notice that I introduce C, right? So C is a constraint, another parameter. Now, this parameter is not something that you want to find, it's something that you define by yourself. So basically, this C will control whether or not you pay attention to this term more or this term more. It's a trade-off between the two, right? So you have the expression for maximize the margin. You have the expression to make the line separate the data as best as it can, right? So in the point that is you maximize the margin and then you have the accuracy. So if C is large, you want to make sure that your line has the high accuracy. But if C is low, you don't care much about accuracy. You put more emphasis on the margin. Basically, you want the model that are more confident, right? So basically, this one is the confident, and this one is accuracy, right? So it's basically a trade-off, right? You want more confident on your model, then you have a small c. If you want your model to be very accurate, then you use a big C. So if you don't want your data to be overfit, you would pick the C based on the trade-off. So picking the C value, normally you can just pick C by yourself, but it's better to pick C using cross validation. What is cross validation? Have you heard of cross validation? So what is the cross validation? Right. So basically you have data, right? And then you have a trend, right? And then you have the test data. And when you want to learn a model, you only use trend data, right? Now in cross validation, your train data is actually separate into a smaller train data and a validation set, right? And basically, you train your data with different C, right? Maybe C equal to 1, C equal to 100, C equal to infinity, something like that, right? And for each model that you train using this train data, you calculate the accuracy in the validation set. And then you pick the C that give you the highest accuracy. Right? So that is the cross validation. Right? And I think the most common cross validation is called fivefold cross validation. So for the fivefold cross validation, right, your training data is separated into 5 groups, right? Each group is like 20%. And then you will have 5 instances, right? So you pick one to be the valid set, and then you do the experiment 5 times, right? So the first time, like this one is test set, the rest is train. The second time, this one is the valid set, and then the rest will be trained, right? And then you do this 5 times. And then you take the average, right? Sometimes you take the average, sometimes you drop the highest, the lowest, and take the average. And that will be the number for just one parameter, right? One try, right? So that is the cross validation. So for example, right, if I pick C equal to infinity, right? So what is C equal to infinity means? Right? If you go back here, if C equal to infinity, it means that we only care about the accuracy. So because we care about accuracy, right? The margin, right? You have fx equal to 0, this is the boundary, right? Fx equal to 1 is the line that are in the closest point, right? From the positive example, right? And then we have the negative, which is the closest to the negative example. So C infinity look like this, right? You have the boundary, you have this margin. Now the same data for C equal 100, right? So for C equal 100, as you can see, right, this point should be inside the boundary. But because C is equal to 100, we allow some slack variable. So this point can be outside. And if you pick C equal to 10, right, you have a very big margin. Right? You have a very big margin, but you allow more inaccuracy prediction. Right? So it's a trade-off, right? So at C infinity, you want to perfect, like near perfect accuracy on the test on the train data, right? And then as the C goes lower, right, you have larger margin, but you are allow some of the wrong prediction, right? And again, when I say like you sacrifice accuracy, you sacrifice accuracy on the training data, which when you report in the paper, you're not going to report the training accuracy. You want to report the test accuracy, right? So it's okay if you predict the training wrong as long as you have a good performance on the test data, right? Because it is a different data. So this is how we use a select variable, right? You have this coefficient that you can control between do you want the margin to be very large or do you want the margin to be very small? So this is the basic of the support vector machine, right? So what you get from the support vector machine, you would get the decision boundary, you would get the W. And you can control the performance with the coefficient C. And then when you want to do a prediction, right? So because this is just the condition for the training data. So when you want to use this on the test data, you can still say like is greater than 0, you have the positive example. Is less than 0, you get the negative example. Right? So you can still compare with positive and negative, right? This one is just for the training, right? You want it to learn something, so you introduce some more constraint. But when you use this for prediction, you only compare with 0. Right? The only time when you compare with 1 is during the training. And because this is written in the linear programming problem, there is like a method to solve this, which I will not go into detail. It's not, sometimes you can use like gradient descent. Another time you can use the like the the Tableau algorithm. You will learn about this in like advanced algorithm class to solve this type of optimization problem. But for us, we will just use, we can write the equation here, and then we just use the package that someone already implemented for us. So any question about classification and decision boundary? So hopefully you understand the basic of classification and the output of the SVM, right? So it's not just you use SVM package and prediction and then see the result, but whatever the number, the parameter you get from the SVM, you should be able to explain the parameter you get when being asked. So this is for today. Next week we are going to do some exercise. So if you want to bring your laptop with you, feel free. So next week is going to be mostly like coding. We will code along and then we will do some exercise together. Also, the third assignment I already post in Mango Canvas. It's going to be a multi-class classification. So not necessarily a label, because you would be what is it? Yeah, it's going to be a multi-class for the assignment. So your answer is going to be like the ID of the data and then 3 numbers. There are 3 classes, and then you have to provide basically the property of each of them. And we will do some exercise next week to help with the assignment as well. I think the score for the first 2 assignment and also the midterm score is already posted. You can check that. I also upload the solution of the midterm also in the Mango Canvas, so you can check that as well. If you have questions about the score or question about whether or not you get credit for which question, you can ask me, or I can show you the work. I think the average is about 14 out of 30. The maximum would be like around 20. The minimum would be 11. All right. So if there are no more questions, I will see you again next week.